Yeah, I can say.
Okay. So today we'll start from the we'll design an adder, okay, and
Okay.
then we'll learn some digital constructs regarding adder and also some digital design like how we design it.
Okay.
Okay. So I have a whiteboard here
Okay.
and A plus B. We want to do A plus B. Let's say we can have any size of adder, right? Like 16-bit, 4-bit, or whatever.
Yeah.
So let's say it's a we design a 4-bit adder, okay. Pen is not there, mouse using very difficult.
Fine.
Okay. So how we do adder, right? We basically we have a 4-bit adder. Let's say we have A3. These are the bits of. It's a binary basically, right? A3, A2, A1, A0,
Yeah.
like
Okay.
that. B3, B2, B1, B0. Okay, we do plus. So how we do? So let's say we generate sum. Okay, A0 plus B0. The bitwise we do, right? Addition. So A0 plus B0, sum 0. It may generate a carry also, right? Because it's a binary number. So 1 bit binary, it can generate a number 2 or 3. 1 plus 1 is 2. So it can generate a carry. So maybe, so we say carry 0, yes, C0. Okay. Like this here, if we all three add, we can generate sum 1 and carry 1. Sum 2 and carry 2. And sum 3 and carry 3. So carry 3 will become a overflow bit, extra bit. So basically, if we add a 4-bit number, we'll be having a 5-bit as some value. Okay.
Hmm.
So so this is like our like. So now we design like how we design an output as 0, how we design an output as 1, carry 0 or carry 1. Okay, and so on. So basically, if we adding these two, it generates a sum 0 and a carry 0, right? If we add these three, we generate the sum 1 and carry 1. And if we add these three, we generate similarly S2 and C2, and we generate these three, we generate S3. So you see, like here in the first level, we are adding just two numbers, okay, just two digits, 2 bits basically, and subsequent on we are adding 3 digits, 3 bits. So it means like so two bits addition is called half adder. So we can say this is a half adder,
Okay.
and this is called full adder. So what we have to do, we have to design one half adder and one full adder, and then we can reuse the same full adder to generate this. Okay, so let's design a half adder first.
Okay.
Create so we have to add a new page.
Okay. Sure.
How to add a new page? It's not adding a new page.
Maybe.
New whiteboard. Okay.
New word.
So this is half adder. Okay. So half adder we saw, right, like A0 plus B0 generates S0 and C0. Okay. So now we create like the truth table for this. So we have to create a truth table for S and C. Okay. So So basically 0 we will not say, we say A plus B in half, one bit, A plus B, C and S, okay, carry and sum.
Right.
Okay. So let's say, so A and B and generates sum and then carry. And these two are input, these two are output. So all possible combinations 0, 0, 0, 1, 1, 0, 1, 1. And 0 plus 0 is like sum, 1 is 1. So sum is 1 and carry is 1, 0. 1 plus 0, again sum 1. 1 is 2. So we represent 0. So sum will be 0. Let's see, any question here, Mr. Trevor?
I think I can hear you, but your video stopped. I think I'm not able to see that entire table.
Can you not see?
Yeah, last two values I think you added there, but I'm not able to see that in the sum and carry.
So video stopped, you mean to say?
So I'm seeing only sum and carry. I do not see any value there.
But here I'm changing the window. You're seeing new windows and all.
Yeah, I can see that. I can see the you created that input and output, and you put the B and A, all the values there. But I'm not able. I think the video stopped. I don't know. The sum and carry column. I'm not sure you filled that or not.
I filled all it. You can seeing my window here and there. I'm changing windows. You're seeing windows changing.
No, I'm not. I'm not.
Maybe I'll reshare. Maybe
Yeah, maybe.
stop sharing and reshare.
Yeah.
So can you see my screen again?
Yeah, I can see it now.
So now you're seeing the whiteboard.
Yeah, I'm seeing it now. Yes.
So now, so 0, 0, 0, 0, basically 0, 1. Sum is 1 and 0 carry 0. This suitable, you might understand, right? This is fine.
Yeah. Yes.
So okay. So now we design a K map to have a like this sum and carry.
Okay.
So two inputs are there to design a K map. So basically two inputs means like four combinations. So here A and B. So A possible value is 0, 1. B possible value is also 0, 1. And this we are designing for S sum. Okay. So when A and B is 0, 0, sum is 0.
Yeah.
When A is 0 and B is 1, sum is 1. When A is 0, A is 1 and B is 0, sum is 1. And when both are 1, sum is 0. Okay. So you see, so when A is 1, we say it's a A. Okay. When A is 0, we say A bar, basically inverted value. So we say where is 1? When A is 1 and B is 0, then 1 is there, right?
Yeah.
Okay. And when other place is 1, when A is 0 and B is 1. So
These one.
basically A B bar plus A bar B. Okay, this is sum. And we say A B bar plus A B bar, this is the equation of XOR gate. Okay, so we can say S equal to A XOR B. Okay, so this sum. Now we design a carry. Okay, so carry K map. A B 1 0 1. So when is carry is 1, only at one combination carry is 1, that is B. Both are 1. Other place is 0 0. So carry equation will be what? When A is 1 and B is 1, both are 1. So A and B. Okay. So some equation we got A XOR B, and carry equation we got A and B. Okay. So now we design a half adder. Let's say not design half adder. We will go for to create a full adder equation also first. Okay. Then we design later. So we add another page. She started video, right?
Yeah, I started recording.
Now full adder. So full adder. What was there, like C? We are having A plus B plus C, because the one carry was also there in carry input also. And we generate like carry out. Basically, we can say carry in and carry out and sum. Two things it generate with the carry. So basically A, B, C in, and generates sum and carry out. Possible values 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1. This will come 0, 0, because, and this is 0. Sorry, this is 1, this is 0. Second one, this is 0. This is 0, 1, 1, 0, 1. This is again 1, 0, 1. Sorry, this is 0, 1, 0, 1. And here 1, 1, 1 plus 1 plus 1 is 3. 3 is actually 1, 1, 1, 1. Okay. This equation came. So now it's a 3-bit input, right? So we'll be having a 3-bit input K map. Here we say C in AB. So C will be 0 and 1. And this will be this will be 0, 0, 0, 0, 1. And when two inputs are there, we always do the changes in gray code. Okay. So after 0, 1, we will not go for 1, 0. We'll go for 1, 1. But only one bit should change when writing a K map. And then here 1, 0. So basically now 0, 0, 0. So what is the value? 0, 0, 0. It's a 0, 0. So sum is 0. Okay. We are designing sum. And when 0, 0, 1. So 0, 0, 1 is sum is 1. 0, 1, 0. So 0, 1, 0. Basically 0, 1 and 0 is sum is 1, and 0, 1, 1 sum is 0, and 1, 0, 0. So 1, 0, 0 here, sum is 1, and 1 and 1, 0, 1. Sorry, sum is 0. 1, 0, 1 sum is 0. And then last one, 1, 1, 0 sum is 0, and 1, 1, 1 sum is 1. So this is the equation K. So so now we write the equation. So basically, so what equation? So this is like AB. This is like AB is 0. So A bar, B bar, A
C.
bar, B B, C, ABC, and plus A, B, C. So this is the equation came, and this is basically so if so now if we make it like simplified it. Okay, so we take A bar common here, right? So you can see A bar is common here. So we take A bar common. Okay. So what will come inside? B bar seen plus B seen bar, right?
Yeah.
And we can take A common here, right? Plus A common. What we get? A, sorry, B seen plus B seen bar. B bar seen. Okay.
Yeah.
So, uh, so what is this like? B bar seen and B seen bar. It's a XOR gate, right?
Yeah.
XOR equation. So we can write A bar and B XOR seen and plus this is what A, and this is equation of what? B seen bar plus B bar seen. It's an equation of X naught. X naught because X naught equation is this B seen bar plus B seen bar, B bar seen both. Okay, so we can say B X naught seen. Okay, and B X naught seen, what we can write? X naught is basically the inverted of XR, right? So we
Yeah.
can write, uh, we can simplify it. We can write here instead of, we can write here XR of naught, right?
Yeah.
Whole naught. So we can write. And now, so what equation becomes? A bar B XR seen A B A bar of B XR seen. Okay, so these are same but bar. So what will happen? One more XOR gate, right?
Yeah.
In the like basically continuation of one more XOR gate will come in condition. So what will come? A XOR B in B XOR C in. Okay, so 3 XOR. So sum in the full adder sum will become A XOR B XOR C in. Okay. Now we'll write the equation for carry. Is amount. Okay. Is it okay, right? Can see, right?
Yeah. I can.
Now see AB 0, 1, 0, 1. So when C is 1, so when B 0, 1 and 1 here, C is 1 here. And when other place is 1, when AB is 1, 0 and C is 1, AB is 1, 0 and C is 1 here. And when other place is 1, when AB is 1, 1 and C is 0 here and here, when all three is 1. Sorry, 1. 1 and here also 1. So rest place is 0, 0, 0, 0. So what did we come? We can make pair, right? You remember we have to make pairs if possible
Yeah.
in K-map. So if possible, where we can make pair where together is there, or both are at the edge, then pair is possible.
Yeah.
Pair is not possible when like they are not consecutive. Okay, so here also pair possible, and here also pair possible. Three pairs are possible, right? So if this pair is possible, so you can see like C is not common. So what is a common in this pair? Common is this one, okay, in this pair. So what is this? This is AB, A dot B plus. In this pair, what is common? In this pair, A is common. Sorry, B is common. B is B. B is one is there, and also C is common. Only Z, only A is changing, right? So it will be a BC, B and C, in, which is common. That will come. And last pair, what is common? A is not common. A is changing. A is not common. So A and sorry, B is changing. B is not common. So A and C in.
See.
So this is a carry out equation. So carry out equation will be always AND of all plus of them. So AND of two bit AND gate plus XOR plus OR gate. So this will be a carry out equation in full adder. So now we got Vivado. So you tried Vivado downloading?
Yeah, I mean it needs what it looks like it is 130 GB something. So that is true. It shows me one.
Yeah, it is very big, but you may not need to download all the like packages. Maybe basic Vivado you can download. Just
Yeah, basic only. I tried this same Vivado ML edition, that thing, but it shows me 130, 129 GB something like that. So I had to check
yeah,
my.
you need space. Yeah, you it like once expanded, it needs a lot of space.
Yeah, so I think I need some more
Clean up.
space in the computer. So I will do it. I will install.
Okay, okay, no problem. So let's create the. So today we are doing adder. We create a project. We say the adder. Okay, RTL project. We don't have any files to say initially. No constraints. You can choose any device. I said before. As of now, create project. So what we have to do? We have to design first half adder, then full adder, and then we use them to design a adder, right?
Yeah.
So we create a source, add basically we create a source. Next, create file. So what will be file name first? For half adder.
Fair enough. Okay.
It's creating the half adder file. Okay, so half adder. So we create ports. Okay. So you see, like by default, it creates a library. Okay. Currently,
Yeah.
we are not using any special package, so we don't need to add other package. But
Hmm.
by default, this package is code. We say A, which is in std underscore logic B. and S sum, this is out, and C out.
So in this we are saying in, out, out, right?
Yeah,
So
yeah. Two
only,
outputs are there, right? Carry and sum.
yeah, so those only two possibilities are there. I mean, in and out. There is no other thing. I mean, only in and out is
There's
possible.
one more is the one more is the in out, bidirectional.
Okay.
In out. One more three possibilities there. In and in out and in out. So in out whenever you use, like when the bus is bidirectional. So bus is bidirectional means like we can I said right try state yesterday I said high bus can be in high impedance state.
Yeah.
So when we design a in out, then the high impedance the bus will be kept in the high impedance, and the when we are driving from outside, then we from inside we'll keep in the high impedance state, and we are driving from inside from the outside it has to kept in the high impedance state. So we'll talk later. This is
Okay.
like also like part of digital design. We'll talk later how
Yep.
when we use the tri-state buses and okay.
Okay.
So since we can directly write the equations here, right? So we don't need any internal signals. Okay, so S will be what we just designed, right? S in half adder. We go here and open the half adder. In half adder, right? So half adder S is A bar B, A B bar plus A bar B. Okay, or we can say AX or B. So we can write both way. We can write the equations. Okay, so we can write. Let's say we write A and bar. We don't write. Bar means not. Okay, not of B
Hmm.
and R. Basically, it become R. Okay, so this is a we have to put proper brackets. Otherwise, it will be not. It will not work. Okay, R B not of B, not of A and B. Okay, so this equation we can write. We can write other way also, right?
Just
Both
so.
A X or B.
Okay.
So we are writing together, but we cannot use both, right? So one we can comment now as of now. Okay. And C we can write C is equation A and B. Okay. C out is there. Why error is there? C out. Okay. We save it. So let's test the half adder whether half adder we designed is correct or not. Okay. We can quickly write the test bench for it. Or we don't write. It's okay.
Maybe for
Let-
full header.
Maybe we can write that test bench for complete adder. Okay. Not this. We design that now full adder. Okay.
Okay.
So we create one more design. Create uh, add source. Sorry, add source. Create file. What's the file name now? Full adder. Finish. Adder. Similarly, ports will be there here. A,
So the standard logic, what does that do? I mean, we can change
it's
that
a
to
type.
specific.
You usually you also have a type, right? When you write any C code or right, you write a type of the variable, right?
Yes, yeah.
This is a type.
Okay. It is like type.
When there's a one bit, right, the type will be standard logic in VHDL.
Okay.
And when it's a multiple bits, right, it will be a vector. So I will show you when we have a bigger adder, right? Currently it's a one bit. When we design the top adder, right, then we'll see the vector, multiple bits.
Okay.
C in, right? We have an input. And C out. Sorry, sum. And C out. Okay. So now what is the sum equation? We remember it. Sum equation is all three XOR A, XOR B, XOR C, and C out is A and B.
Oh,
C is not there. C in is there. That's why error is showing. R plus means R. Okay, so R, B, X, B, and C in R, A, and C in. Okay, so now this full adder is done. So now you see, like, I'll open the whiteboards. You see, right? We want to design 4-bit adder. So uh, how many adders are it is using? It is using one half adder, and how many? 3 full adder, right?
ladders, yes.
Yeah. So what will be input? Like, if you want to design input, so there'll be a 4-bit input, A and B, and then no carry in, because basically at this level there is no carry in. Intermediate carry is there at each level. At this level there is no carry. Okay. So we want to design a adder, final adder. Okay, which will use this to have a designed it. Okay, so add source.
So we created a half adder, then after that full adder.
Yeah,
Then
and then we will combine it, use it. Basically, we remember, right? As yesterday we were showing, like, instantiation component. We yesterday, remember, we designed a component, the test bench.
yes.
So half adder and full adder will become a component to have
Oh,
a bigger adder. Okay.
okay.
So now we design adder. Okay.
So we created separately half adder and full adder, right? So
Yeah,
cannot we create in only one file both half and full adder?
you can create, but it's a two different component, right? You can
Okay.
file can be same, but still entity will be two, right? So
In the
it's
same.
always like it's recommended basically to have a use of
Re-
uh, means basically we want means it's not mandatory to have a same file name with the same entity, but it's easier to manage the file and entity if we have a same file name and say with the entity. So
okay.
if you want to have a same file name with the entity, definitely have to keep two files, right?
Mm, yeah.
And it's easier to manage. You don't never ever design a very big logic in a single file until unless it's required, really required.
Okay.
So you try to break your like that is a good strategy. We try to break your design in a small like blocks,
Yeah.
and then those small blocks is created separate and then connected.
Mm,
Don't try to write a big code in a single design, and then you'll be like uh, it's highly impossible to write. I mean, that is not good design.
okay.
So as small as you can make it, It is very like you
Better.
can say means easily readable, easily understandable, and tool also like means basically it's like optimized one. So it will be really optimized because you can see it what is done.
Okay, so this one more question. We are creating this full adder, right? So
Mhm.
does this library provides by default, like if I want to import full adder from the library?
So full adder is not like it will not use the library. It will use this function. It will use this gates.
Yeah, I mean this.
Yeah, there's a adder in library. So if you
Okay,
want, you can do this way directly. This possible. So I
okay,
will show you. I mean, when I design, so I'll show you. So what we have like we have a and B, right? Input
yeah,
A input. A input is what? Now it's a 4-bit input, right? We say so. We say std underscore logic underscore vector. So you can see vector is there, and vector is how many bits? 4-bit. So we say 3 down to 0. Okay, this is a vector. So you can write both ways. Both ways fine. 0, 2, 3, or other way 3 down to 0. Both ways fine. But we always recommend to write MSB for MSB. Like 3 is called MSB, right?
yeah.
So max bigger number is we want to put as at the MSB level. So and always LSB means smallest index we want to keep at the right side. So that's how we always keep it down to 0. Okay, this is like a way. It's not. It's a recommended, not mandatory. You can have a 0 to 3. It's fine, but recommended is like you use down to create a vector.
Okay. So this is our final. I mean, we are
Yeah,
in this
final,
final.
final,
We are
final.
going
Yeah,
to.
final.
Okay.
And B is std underscore logic underscore vector. And what is the output? S sum is output. Out. So sum will be what? Always 1 bit extra, right? Because carry out is there, right?
Yeah.
Because you see there is always one carry is possible, right, at the last. So
Yeah.
sum 4, basically sum 4 is also possible, right?
Right.
Basically, if we add this, what will be this? This is sum 4. Okay,
Yeah. 2 bits. Yes.
not 2 bits. This carry will be we add two number. There is always possible a carry, right? So this carry we have to take into account, right, as output. So
Hmm.
this carry final carry will become a sum 4, right, in the full in the complete adder, right?
Yeah.
So sum will be always 1 bit extra than the input. Okay.
Yeah. That is 4 to 0.
Okay. So now we want to use the half adder and full adder, right, to create a like this adder, final adder.
Yeah.
So we take the this port and create a component there. So half adder is component half adder is and port and end component. Likewise, full adder is also there. Copy it. So two components are there. Okay. So now you remember we this is just a like declaration of component, or we can say it is visible now. Now we have to connect the component to this component to these bits, these inputs we have to connect, so that we will have a final output. Okay. So how we can connect it? So you
That
remember you see in the whiteboard, like how many we want? One half adder we want and three full adders we want. Okay. So we take one half adder. You remember yesterday we did port map, right? To map the to do the connections.
yeah.
So half adder. So you remember I give a instantiation name. So we can say
Yeah.
instantiation name can be anything. I underscore half adder. Okay. Instantiation name and then half adder, and then we do port map. We say port map, and then we remove this. For doing connection, we do like this, right? Connected to the this, because this AB is local to half adder, and something will should be there in the adder to connect it. We'll do that. Yes. Okay. So now you see here in the whiteboard, what is there in the half adder? Two inputs.
Yeah.
What is, you can see A0 and B0, two inputs are there. And what is the output?
Yes.
S0 and C0 is output, right? C0. So I can say A0 means this A, find this entity A and B, and this is S sum. Okay. So A is zeroth bit. So we can select the zeroth bit using the bracket. So this is how we can select each bit in the VHDL. Okay. This is zeroth bit. Okay. And then similarly B zeroth bit. Okay. And then it will generate a S output. So it it will connect to the S output. Okay.
Okay.
So S0 it generated, but now we have a carry also, right? C0, C1, C2, C3 also there, right? So this is like a intermediate, right? This is not at the port level. It is just the intermediate. C is intermediate, right? C0, C1, C2 is intermediate within the local variable. Basically, it's not a port level. So we have to create a variable basically to connect the C.
Okay.
So let's create a variable. You remember I said like variables or signals should be created within the architecture and the this begin level.
Mm.
So we can create a signal C, and signal C, and signal C is how many bits? You can see it's also 4-bit. C0, C2, C1. Okay.
Yeah.
So C is 4-bit. std underscore logic vector e down to 0. Okay. So you see it generates a C0 output. Okay. C0 output. Okay. Half adder generates a C0 output. Now we use the full adder. Okay. Now we have to use 4 full adders. Okay.
Mm. Yeah.
3 full adders. So 3 full adders. So let's give a name. Okay. I is like I0, we can say I0, instance 0. Similarly, instance 1. We can say, because just we can give a number because we are using the full adder, right? So we have to give a different name. Okay. So instance 1 full adder port map A. So you see the inputs are here A1, B1, okay, A2, B2, A3, B3. And what is a carry input? Carry input is output of half adder, okay. This
Yeah.
carry input is output of previous full adder, okay. So here it will become A1, B1, and this will become, this is output of previous, right?
Yeah.
The output of half adder basically. So this will be C0. Okay. This, so this C0 output is connected to input of this, and this generates S1, and this again this will generate carry out. So carry out for the next full adder. Okay. So C1. Okay. So now, so this, how many full adders we want? Four full adder, three full adders, right? So we copy it, we repeat it. One
So
instance.
we cannot write for loop like
Yeah,
that
you
too.
can write. We can write. I will tell you. I mean, this, that is not for loop. That is a different thing. I'll tell you. So I will first do this. So there's one statement. This is I2, I3. Okay. I will teach. I mean, tell you all those things. So this will become 2, 2, 1, 2, 2. Okay. And this will become 3, 3, 2, 3, and this final carry will be basically the sum 3, sum 4 basically. You can sum 4. You see here, sum 4 is basically the same C3. Okay. So basically we are not using C3, so we can reduce one bit from here. We can use 3 bits only, right?
Okay.
No need to have a declare a extra bit if you are having only 3 bits. So now the adder is done. So you see, right? Still the three. Still it's showing the. No, sorry, now it's created. So you see, as we connected all and saved it, you can see the hierarchy is showing here. So adder is there. It is using one half adder and three full adder. It's showing here.
Yeah.
As we connected, the tool identified it. We have connected in the code, and this already showing the hierarchy here. Okay. So now we create a test bench. Okay. So we go to a simulation source. We can create a test bench, add source. We can create a file. We can give what name? TB underscore adder. Finish. You see the TB adder is showing here. We
Yeah.
go to this file. You remember, like, add test bench don't need any ports, so we don't add any ports. We just use the adder port, full adder, sorry, adder ports. So we copy it, adder. Go to TB, we declare as a component. End component. And then we take this, which we connect it. Okay. So we can say I adder and port map. We have to drive A and B, right? And to drive it, we have to have some local variable in the test bench to drive this A and B. Okay. Okay. So let's say we have to connect it. We have to declare some local A and B, right? The signal A std and copy it because same thing. A B S. Okay. So now we connect it. A will be connected to A of test bench, and B will be connected to B of test bench, and S will be connected to S of test bench. You remember one thing like uh, why it's error? Oh, here U logic is it. So see, it's giving us error. I selected a wrong std logic, right? Std underscore U logic. So it's giving error because the type of A, this A is std underscore logic, and type of this this A is U logic. U logic means unsigned logic, and A std logic means not unsigned. So this will be like U log. Means we have to remove U, so it will not give any error. So now you can error. So basically the type should match, otherwise it will give you error. So type of the connection should be a same type, whatever the variable is there in the other module. Otherwise it will give you error. Type should match. So now
So
we drive the, yeah.
that unsigned and signed, I mean, why do we have to use unsigned there? Like U logic, we say that.
So and basically we should have a type, right? Otherwise let's say we want to define a variable, right? Uh, in future we'll be having a complex, right? So we will not design a half adder or full adder. We'll be directly using the libraries packages to perform arithmetic operations. So signed operation, unsigned operation, plus, minus, multiply. Directly we can use the operators from the VHDL language itself. We don't need to design it. So in that case, we should have a proper, like we want to design unsigned logic, we have to use unsigned vector, right? That's why U logic vector.
Okay, it is for like then to represent the negative numbers in the binary.
Yeah. So currently, like this is the like std school logic have all the types within it. It can represent everything, but U logic will represent a subset of it.
Okay, only specific to that
Yeah,
site.
yeah, yeah. So now we drive it, process, and so you remember we drive a we can, it's a 4-bit input, right? So we can give some input 0001. B is 0001. Okay, so it's two values. So and then we say wait for, let's say 1 second. We copy it to do quickly. So let's change the value here. A is 111, and let's say this is 1011, and let's say 1 here, 99, and let's say all ones.
So we have the 4 bits, right? So it has the it can have 0 to 15 numbers. I mean,
Yeah, 0 to 15 value each number. So we can, so there may be hundreds of vectors are there possible.
so does it
To
so does it do? I mean, does it can it do it automatically all the possible values, or we have to manually add this
we have to
combination?
do no, there's a way. So I'm not like we can do a loop here. We can do a different way also. So currently I'm not telling you. I mean, slowly
Okay.
we'll move. Okay,
Okay.
how to define that? We can definitely do a loop, and it will do a plus one, plus one, plus one, plus one, and test all.
Okay. Hmm.
Or we can define a random value also, random number. Okay,
Hmm.
so it will keep a random value there, and then
Okay.
uh,
Hmm.
let's say this is 1 1 and then 1. Okay, so now save it, and now we run it. Okay, run simulation. See, I did not initialize a value, so you say you are seeing like u everywhere, right?
Yeah.
So remember yesterday I was doing the initialization here,
Yeah.
yeah. So I did not initialize it, so it's showing uninitialized. Basically, and one more thing, like this initialized value is just a simulation only. It will not impact any hardware. So hardware wise, the initialize value and weight, these are not used in the design. You should not use in the design. This is a test bench only you should use. Weight you should not in the design.
Okay, the hard-coded values should be in the test only.
Test bench only.
Oh,
You can use the hard coded value like this, but uh, but basically initialized value will not be taken. This is okay.
yeah, I mean, this is just for testing, right? I mean, it
Yeah, just
doesn't.
for testing. Yeah. So I will tell, means later future will learn like what we cannot use it, what we should not use in the in the design, and what should use it. Basically, this is only for test bench. Wait for, not for the design. Okay. So we run it. Let's run it for some time. Run 10 nanosecond. Why it's not showing anything?
In the
Oh, the error. That's why it's not showing. See, error is there. And one more thing, we forget it. You go to the source. So you see, right? We did not do. We have to do this as a still error is there. Why? To end process. I forgot. No error. So you see, like we have to run it. We have to make a top file. This currently top file is selected. This, so that's why nothing is driven to here, and we are running it. Nothing is driven. Nobody is driving it. It's running whatever top is selected. It is running that only in the simulation. Okay. So you have to make this as a top file. Set as top. As first of all, error is there. Why error is there? You have not saved. Okay, now error is not there. So once error is done, still top is showing this, right? It will, oh, now automatically it's making top this. Okay. So now we run it. It will run this TB in the. We have to close the simulation. So we have to close the simulation. Close simulation. So it was giving error, so we closed it and run simulation. Launch into earlier errors. Okay, so error is there. TB error 55. Expression has 4 elements. Oh, here. I say my type. You say here 4 down to 0 is there. So type is mismatched. Let's give error. So basically, some things it will not show you here error. Basically, the syntax wise, but it will give you error while elaborations because it cannot map the 3 bit to the 4 bit. So it give you error in the elaboration error. Yeah. So now it ran. You can run for maybe some 10 seconds more. Let's see the waveform. Zoom out. So you see, like, let's one more thing I can show you, like how to use, like currently we are giving binary value, right? So we can change. Currently it's showing in the hex, the waveforms. Okay, we can change the this waveform, anything. Radix is there. Radix, we can change it to binary, hexa, or decimal also. Okay. So
Mm.
let's change it to binary first. Okay. So this is how we given the numbers, right? 0, 0, 1 and 0, 0. So 0, 0, 1, 0, 0, 1 is like 1 plus 1 is 2. So 0, 0, 1, 0, right? And then 1, 1 plus this is 3 and this is 9. 9 plus 3 is 12. 0, 1, 1, 0 is 12. So to better have a good visibility, we can like make it radix to unsigned decimal. Okay, unsigned decimal. So you can see clearly. Okay, so 1 plus 1 is 2, 3 plus 9 is 12, 15 plus 15 is 30, 9 plus 9 is 18, 1 plus 1 is 2. Okay, so you can see like the sum is working fine. Okay, any question until simulation?
So let's say, so now we are going one by one, testing it, checking it, like 1 plus 1 is 2, then
Yeah,
15 is 30. So let's say we have so many values here. So in that case, we cannot check one by one, right? All of these values. So in that case, how do we make sure that this is the giving the correct?
fully correct value. Huh?
Yeah, I mean, how?
You mean to say
So,
how we test like this the value is correct or not?
yeah, I mean, these are like very few values now. We can test it manually, right? One by one. If
Yeah,
there are
one by one. So means I will teach you. Maybe it's very early to say.
okay,
Because because once I will come up with like counter, how we can generate like a counter, right? Or we
okay,
can generate a random values. So different constructs are there like we will use in future. So definitely, as you say, right, there is a very limited value. We can test definitely all values, and very simple way we can test all values, like create a counter, create a random number, and run for more time. And then we can test like whether the plus, because we cannot see the waveform always, right? We can have a self test check, self checking test bench. So we can even have a reference value and match it, whether a reference value is matching with the generated value or not. The reference value, what is the reference value? Currently we have created the hardware of A and B, right, by ourselves.
yeah,
But instead, so in the test bench we can have like plus value, instead of in the design we are doing using half adder full adder. In the test bench we can use a plus b directly and then match the value. Okay, that kind of thing can be done.
mm,
uh, we can do later this, maybe next class maybe we can focus on this only. So
okay,
like you said, do you have two questions, why how we can use the loop? Okay,
mm, yeah,
in the design, why you're using the four instances. And in next class maybe we can have like, uh, currently we have fixed the values, right? Only 3-bit adder. Can
yeah,
we have a can we have a generic adder? Can we have a, like the same design which works for 4-bit adder, which works for 10-bit adder, which works for 16-bit adder? Can we have that?
mm,
So that next class, uh, we can do this generic plus having a full self-checking test bench, those kind of thing. Okay.
okay.
And also, so maybe just to recap, what you learned. I want to ask you what you learned in terms of like design and in terms of language.
So
Just
we first we want to create the full adder, and for that we
like,
created the,
no, no. I'm not telling the full ad. I just want to understand in terms of like design method. What you learned in that in terms of design method, and what you learned in terms of language. What topics you learned? Topics I want to say.
so like we created the full adder with using one half adder and three
No,
full
no,
adder.
that is specific to adder. I'm asking question like you should say like I learned how to design logic using Carnot map, truth table, and then coming up with the equations. This you learned, right? The
Yeah,
full adder is just an example. Maybe I can give you homework and I can say, can you design a 4-bit comparator? then using this knowledge, whatever you learned, can you
Okay.
try it? At least on the paper, can you give an equation next class, like full adder, 4-bit comparator equation? Can you try it?
Okay.
So this may be a homework, like not that coding part, at least because coding to do coding you need this tool. Maybe still you have not installed a tool. Maybe this is one part, like design part. What you learned in terms of language. I just want to, because there's multiple things I have shown you in the language. Just I want to understand from you what you learned in the language till now.
Uh, how to declare the inputs
Yeah.
and what are the output and how
Okay.
we can uh, pass the, I mean, how we, if it is a single value, then we can have the we do not have to use the vector there. If we
Yeah.
are passing multiple values, then we use the vector
Yeah.
uh, based, and we can create the we should always create the small components to build the
Yeah.
bigger component.
Yeah.
uh, and also we can based on this we can create the test bench for the
Mhm.
component and test it.
So just to summarize it, from my side, what you learned in the test bench, in the design, you learned ports, entity, architecture part, where and what we should declare in the architecture and what we should declare in the design part. And in the design part, you learned like how to instantiate a component in a hierarchy, and
Like,
also you learned how to write a test bench, a basic test bench. Okay, so these four things you learned now, as of now. And next time next class I will teach you how to write a efficient way, the loops, not loops, the instantiation loops. You said, right, I am instantiating 4 times, but can we
yeah.
do in loop? Okay, that we'll learn. And then we'll learn the test bench, to have a self-checking test bench, like how we can write a self-checking test bench to check all the values, possible values. Okay.
Okay.
And also if you can create the equations for the comparators, we can
Okay.
do coding for that comparator in next class.
Like 2 bits, 2-bit comparator, 4-bit comparator.
4-bit comparator.
Okay.
It's a simple, right? You go and design the k map, and what will be the output? Equal to, greater than, less than, or equal. Three outputs: greater than, less than, equal.
Yeah.
Okay,
Yeah.
3 outputs and 4 inputs. Or you
Yeah.
can to simplify it, maybe go for 3-bit input only, or
Oh.
2-bit input. If you want to have a keep simple, let's do a 2-bit.
Okay.
Okay, 2-bit input and 3 outputs.
Yeah.
Okay,
Yeah.
and just to show you elaborated design, let's say maybe. Okay, I'll elaborate. Open the elaborated design. So it will show you how we connected it.
Yeah.
So you see, we
Yeah.
have connected two 8-bit, two inputs. AB is there, and 4-bit sum is there, 5-bit sum is there, and then 1 half adder and 3 full adders are there. Right? It's showing your design, and you can see what is there inside the half adder. This is there. Okay. So we currently designed with the AND gate, right? You remember we did AND gate.
Yeah.
We commented the XOR gate, and we just uncomment the XOR gate, and here half adder. If you just uncomment this, still the values will remain same. And we if we do just reload design, reload. Okay, so it's reloading, it's elaborating again because we changed the design, right? So it's doing the re-elaboration. See, half adder XOR gate, right?
So with Excel, yeah.
Okay.